All right, so when you're writing ionic formulas, it's important that you're going to have to distinguish if something is ionic or covalent. So you're going to have to go back to a few chapters ago. We learned that ionic compounds are formed between metals and nonmetals. Okay? Because if you come across a covalent compound, the naming rules are different, and we'll get to that after we go over the ionic naming rules and ionic formulas. So when we write ionic formulas, the compounds must have no overall charge. That means a net charge of 0. That's the same thing as a net charge of 0. So how do we get a net charge of 0? Well, if you combine sodium and chloride, one's a cation, one's an anion. Sodium is a metal. Chloride's a nonmetal. Sodium has a positive 1 charge. Chloride has a negative 1 charge. And so when you add positive 1 plus negative 1, that is 0, and you get no overall charge. That is a net charge of 0. Another example is magnesium oxide. And so magnesium oxide, magnesium is a metal. It has a positive 2 charge. Oxygen is a nonmetal. It has a negative 2 charge. When you add positive 2 plus negative 2, there is no charge. It's 0. And so the formula is simply MgO. MgO. And let me write for sodium chloride, it's NaCl. Now, what happens if you have ions with different charges, like calcium and chloride? Calcium has a positive 2 charge here. Chloride has a negative 1 charge. Their overall charge, when added together, must be 0. And so 1 calcium ion combines with 2 chloride ions, and we get CaCl2. And so the compound's name is calcium chloride. I'm going to show you a shortcut in a minute once you understand how this is done. I feel like we did a little bit of this when we were doing Lewis structures well, I know we did it last year. That's when my physical science runs together with my chemistry, and I start to get fuzzy on what I covered in what class. So I can't remember if we did some of this with our Lewis structures in here when we were doing Lewis structures of ions. All right, so since calcium has that positive 2 charge and Cl only has the negative 1, you need 2 Cl's here that carry a negative 1 charge to balance out or to cancel out that positive 2 from the calcium. Notice how we're putting the IDE ending on the anion's name. And I also want you to notice that when we write these formulas, the metal or the cation always comes first. Okay, so we would not write Cl before Ca. The metal or the cation is always the first one written. That's very important. The second one is always the anion, which is the nonmetal. So what if we try to combine sodium and oxygen? Their overall charge must be neutral or 0. So now if we have oxygen carries a -2 charge, we need 2 sodiums in this compound because each sodium carries a +1. So when you add these up, +1 plus +1 plus -2 gives you a 0 charge. And so our chemical formula tells us that we need 2 sodiums, that's what that subscript 2 tells you, and 1 oxygen. So just like the charges, if the charge is +1, you don't write the 1. If there's only 1 atom in the compound, you don't write a subscript. You don't have to write the 1. So if there's no subscript, you know there's only 1 of that atom. And we would call this sodium oxide. So you keep the stem name for oxygen, and then you change the ending to IDE. It's not oxygen and I, it's just oxide. All right. What if we combine aluminum and oxygen? Aluminum is a cation. It has a +3 charge. Oxygen's an anion. It has a -2 charge. The name is aluminum oxide. How are we going to write this formula? How are we going to add +3? What are we going to do to the amount of aluminums and oxygen so that the +3 and the -2 are going to equal 0? Let's go. Okay, very good. All right. An easy way to do this, there's a shortcut. If the charges are different, you can do the crisscross method. Did you notice how this 2 came down here and this 3 came down here? You just switched the numbers and they became the subscripts. Now you're not changing the charge on aluminum and you're not changing the charge on oxygen. Now you're saying you have 2 aluminums that carry a +3 charge, and now you add them to 3 oxygens that carry a -2 charge. So that's +6 plus -6 equals 0. So now that you have a net charge of 0, the formula is Al2O3. And this is aluminum oxide. So you always keep the full name of the cation. And you're just changing the ending of the anion to IDE. Okay, let's try another one. Calcium and fluorine. So we know that calcium is a metal, so it's our cation. Carries a +2 charge. Fluorine is a nonmetal. It becomes an anion. It carries a -1 charge. The name is calcium fluoride. What is the formula going to be? Maria? CaF2. Now, if you want to do the crisscross method, again, look how the 2 from the calcium is here. And then since there is no subscript there, we know that's a 1. It's just an understood 1. Yes? No. It always works. Now, we'll get to something more complicated. If you have a 4 and a 2, you must simplify it down to the 1 and the 2. So, if you end up with subscripts that have a common, a greatest common factor, you're going to divide by the greatest common factor. Simplify it. Does that make sense? Yeah. But otherwise, it always works. But you must simplify if it can be. All right. So I'm going to show you the math here just in case anybody's getting lost. So for calcium, we have 1 atom of calcium now in this formula. Calcium still has a positive 2 charge. Now we have 2 fluorine atoms, which carry a negative 1 charge. And so positive 2 plus negative 2 equals 0. There's the math on that. So that's how the crisscross method works. So when you have 2 different charges, you can just crisscross. All right. Transition elements, we know, form cations because these are also metals, transition metals. And we know that metals form cations. And we know that many transition elements form cations with more than 1 charge. That's why we use the Roman numerals. And so, for instance, copper, and this is in your reference table in your book, in your chapter 9.1 section. We could have copper with a positive 1 charge or copper with a positive 2 charge. And the Roman numerals tell us the charge for that particular copper that we're looking at. All right, so, looks like I already did this one, but this is an example. If we have copper 2 and chloride, that means copper 2 has a positive 2 charge. And then we know that chloride is a group 7A element, so it has a negative 1 charge. The formula would be CuCl2. Again, if you crisscross the charges, you come up with CuCl2. And the name of this is copper Roman numeral 2 chloride. Notice, many students will get confused and want to use Roman numerals in the formula. Roman numerals are only used in the name. So the formula does not use Roman numerals. The name does. Madison.
With a copper 1 ion, could we just leave out the Roman numeral, or do we have to put the Roman numeral?
You have to put the Roman numeral because when someone sees the Roman numeral, that tells you that, oh, copper is one that has multiple charges. If there is no Roman numeral, that means it's a transition metal that does not carry multiple charges. Yeah. Good question. Okay. Cut some of my slide off here. So here's another example of a transition metal, ionic compound. Iron, Roman numeral 3, and oxygen. So that tells us that this is iron with the positive 3 charge. We know oxygen being in group 6A carries a negative 2 charge. And so again, if you crisscross the charges down, we get Fe2O3. So that does not mean that the charge on the iron now is 2. That means we have 2 iron atoms. Iron still has the positive 3 charge. And now we have 3 oxygen atoms. And when you add those together, we get a net charge of 0. Because the 2 irons times the positive 3 gives you positive 6, plus the 3 times the negative 2 is negative 6, added together that's 0. The name is iron 3 oxide. And then another example that I've done down here is iron 2 and oxygen. So iron can have 2 different charges. And that, again, that Roman numeral is distinguishing that here. And so for iron 2 and oxygen, our formula is FeO. FeO. All right. I'm not really sure why I have a video attached here. This is an old. I'm going to see what that is. Does it work? Let's see what this is. I didn't preview this today, but
Sometimes when you look at a chemical formula, it can be difficult to tell what the charge on the metal ion should be. Now, if you have a representative metal, like barium here, it's pretty easy, because barium is in group 2A on the periodic table, so it always has a 2+ charge when it ionizes.
So, I've just told you all that, so I've got that. I'll post it on Edmodo if I think it's something useful for you all. I'm going to see. I'm going to have 40 slides on this. I don't know if I want to get into polyatomics or not. Let me see. I want to look at your book right now. Okay, we need to talk about what is a binary ionic compound. Okay. Yeah, I'll save polyatomics for another day. We'll do that tomorrow. Let me get back in here to the student text, though. What signed me out of the student text? Okay, let's do these sample problems. Okay, let's talk about the word binary ionic compound. I'm going to add that term to the word wall. Binary ionic compound. What does the prefix bi mean? 2. Binary ionic compound. So, all of the examples that we just worked were binary ionic compounds. There were 2 ions. We had one cation and one anion. And so sample problem 9.2 on page 273, we are writing the formulas for binary ionic compounds. So example number 10, A, Ba positive 2 and S negative 2. It wants you to write the formula for that. So what would our formula be for that? Someone said B, A, S. Exactly. What about lithium and oxygen? Li positive 1 and oxygen negative 2. Look at that one. McKenna? Li2O. Very good. And then C, calcium, which has a positive 2 charge, and nitrogen with a negative 3. Look at that one and raise your hand if you think you've got it. Madison?
C3 and 2.
Very good. Ca3N2. And then the last one here is Cu, copper, with a positive 2 charge, and I with a negative 1 charge. What do you think that one would be? Peyton? Cu, I2. All right. There you go. You're writing formulas for binary ionic compounds. Now, in 11, it's giving you the name, and it wants you to write the formula. So A, bless you, gives you sodium iodide. So now you got to use your periodic table. Look up the element symbols and put the correct endings. Anybody want to take a stab at A? Sodium iodide. I'm sorry, not put the correct endings. Put the correct symbols and subscripts. Mallory? Okay, so NaI. So you hopefully saw that sodium carries a positive 1 charge because it's in group 1. Iodine is in group 7A or 17, so it would carry a negative 1 charge. So it just becomes NaI. Stannous chloride. I'm trying to remember. This is the classical naming system. I will not give you one like this because I said we are going to use the stock system. You know what? I'm skipping that one.
It's 10.
It is 10, but the ending OUS and IC are used for either 10-2 or 10-4. Do you have your reference table there?
It's 10.
Is it 10-2? Okay, so the us ending is for the 2 charge. Okay, so if I were to rename this, I would call it 10 Roman numeral 2 chloride. I won't use stannous. How would you write the formula for that one? Elizabeth?
SbCl2.
Say that again.
SbCl2.
SB?
Oh my God, SN.
SnCl2. Because if you look at 10-2, it carries a positive 2 charge. Chloride carries a negative 1 charge. That's how we got SnCl2. 10 is one of those elements that gets its name from the Latin derivative stannous. And then potassium sulfide. Alex Herm?
N2S.
N?
Or Na2S.
Potassium?
K.
K. K. Okay, so sulfide, sulfur is a negative 2 charge, K is a positive 1. Yes, that's correct. And we'll do the last one and stop. Calcium iodide. Carol? Just CAI? What's the charge on calcium? CAI2. Because calcium has a positive 2 charge, iodide has a negative 1. I won't give you any homework tonight, and then we will move on tomorrow and continue working on these.